we're talking simplifying limits of indeterminate forms yesterday. So we left off, remember we were saying, this is the one we left off on, right? And this is just a pretty straightforward L'Hopital's rule problem. So we verified that this is one that looks like an infinity over infinity, right? If we evaluate this directly, as x approaches 0 from the right, we said that cotangent of x would approach positive infinity, and log x would approach negative infinity. And the reason was because of the shape of this log graph, right? And you guys might be a little rusty on that, but you want to get familiar. Like when you think log x, just in your mind, you're thinking that graph, and that helps a ton, right? So on this graph, we can see the domain of a log function is just only positive values of x. And as we approach 0, we can never get to 0, but as we approach 0 from the right, the output value, the value of the function approaches negative infinity, right? So this is classic L'Hopital's rule. We're just going to differentiate the top and differentiate the bottom until it's no longer indeterminate. Okay, well, after one step, it is indeterminate, right? Because what is the value of cosecant x as x approaches 0 plus? Cosecant's 1 over sine, right? Think what a sine function looks like. Let's go back to the unit circle for a second, right? If we think unit circle, as x approaches 0 from positive values, isn't that just going to be a really small angle right there? Small positive angle. Well, what's the sine of a very small angle going to be? It's going to approach 0, isn't it, right? Positive 0. And so I'm going to end up getting, 0 squared times negative 1. I'm just going to get a 0 on top, aren't I? Right? On the bottom, obviously 1 over x as x approaches 0 plus is also going to give me, that's going to give me what on the bottom then I'm going to get? Oh, why did I say 0? That's going to be, cosecant is 1 over that, so that's going to be infinite, isn't it? Right? You get my point? Sine is going to be approaching 0, so cosecant is going to be the reciprocal of sine, so I'm going to get 1 over a really small value, so it's going to be infinite. I'm going to get infinite on the top and infinite on the bottom, and we don't care about the signs. We just know we have some infinity on the top, some infinity on the bottom. That's indeterminate. So we got to go again. Okay, but we don't want to be hasty about this. We want to be smart about taking this limit. Is there something we could do to the argument of the limit? In other words, what we're taking the limit of to make that process easier. Right now, it's not like we could do this, but taking the derivative of cosecant squared, that's going to be a chain rule problem that's going to involve derivatives of cosecants times cosecants, agreed? That doesn't sound great, does it? Right? Okay. 1 over x, that's x to the minus 1, that's going to be a chain rule problem. Or quotient rule, if you really want to use quotient rule, right? What could I do to make that better? What's in the orange bubble? Because the limit doesn't care what's in the orange bubble as long as they're algebraically equivalent. I can rewrite that ratio in a more convenient way. Like 1 divided by 1 over x just equals what? X, right? Yeah. 1 over x is just x. Okay, cosecant of x, you already told me, is 1 over sine, right? So couldn't I rewrite this, everything in the bubble? I could just write it as I've got my negative, but the x is going to go to the top, and I'm just going to get a sine squared x on the bottom, right? Isn't that better? I think that's better. Okay, so now we could apply L'Hopital's rule again, because that's indeterminate. Okay, so what does that equal then? The derivative of the top is what? Negative 1. That's a good sign, isn't it? What's the derivative of sine squared x? Sine squared x. What's that gonna be? Everybody agree? 2 sine x cosine x? Give me thumbs on that. You guys, thumbs up if you agree, thumbs down if you disagree.
Why not 2 sine?
Right? Well, what's the outermost layer in that derivative? Squared, right? Derivative of hand squared is 2 hand, right? So the first step's gonna be 2 sine x. What's the next layer? Sine. Okay, so derivative of sine is cosine. Okay, good. So that's gonna give me a 2 sine x cosine x. Okay, let's see what that gives me now. If I evaluate this at 0 plus, what's that going to give me? I'm going to get negative 1 on the top. What am I going to get on the bottom? I'm going to get 0, aren't I? Oh, whoops. Thank you. Yeah. Okay. Right. What's that going to give me? So I'm going to get, on the bottom, I'm going to get 2 times, what's the sine of 0 plus? This is good review because we're doing limits, infinite limits here. What's the sine of 0 plus? 0 plus, right? Everybody agree? That's 0 plus. Sine of a really small angle is going to give me a really small positive value in quadrant 1. Okay, so we'll just call that 0 plus. And what's the cosine of 0 plus? 1. So on the bottom, 2 times 0 plus times 1 is just 0 plus, isn't it? 2 0 plus is 0 plus. So I end up with negative 1 over 0 plus, which is what? Yeah, a 0 on the bottom gives me an infinity, right? 1 on top, 0 on the bottom gives me infinity. So this part, I gotta be real careful here. Oops, the color coding is critical here on this one. So that part right there gives me an infinity, and this part, negative divided by positive, gives me negative, right? Done. Okay. So we had to do 2 iterations of L'Hopital's rule, but we got our answer. Okay? All right, so next step. The AP test does not go further with L'Hopital's rule than that. All the AP test does is deal with these types of forms of L'Hopital's rule. Okay, I think that's a huge mistake though, because you use L'Hopital's rule all the time. And in your college calculus classes, that's one of the first things you're going to do when you're simplifying limits of indeterminate forms, is you're going to extend beyond that to things like that, for example. 0 times infinity is also indeterminate. Okay? It could range from 0 to infinity or somewhere in between. So what's our strategy for this? Any ideas? That doesn't look like L'Hopital's rule, does it? L'Hopital's rule very specifically deals with a ratio, right? Okay, so what do you think? Can you think of a strategy then? You got an idea, John?
We just take the derivatives and we can get like 1 over x. Or,
Okay, but if we're trying to, now think about what you're suggesting for a second here, because we're saying the limit of that, right? That's what we want to find. If I differentiate that, the derivative of that is different than what we started with. And I'd be taking the limit of a different kind of function then, right? Now that's different than L'Hopital's rule, because with L'Hopital's rule, we were taking the limits of the top and the bottom because we're guaranteed that if this limit is indeterminate, when we take the derivative of the top and the derivative of the bottom, even though that's changing the function, we know that those two functions are going to happen to have the same limit, guaranteed by L'Hopital's rule. That's really what L'Hopital's rule did. Remember at the end of the day yesterday when we graphed those two functions, the function that we started with and then the ratio that we got after applying L'Hopital's rule, and they were totally different functions. But what was true was their limits were the same. See my point? L'Hopital's rule only guarantees that's going to work if we start off with functions that look like 0 over 0 or infinity over infinity indeterminacy, right? If we differentiate some other function that doesn't match those forms, there's no guarantees, right? So we can't just differentiate. Okay, but let's just think conceptually for a second about that. 0 times infinity. How could I turn 0 times infinity into a ratio? And let's use as a model. What if I just multiplied like a times b? I said model, I meant ratio. How could I turn that into a ratio? How could I turn a times b into a ratio using a's and b's? Yeah, I could do a divided by 1 over b, right? Does that make sense? I could write that as a divided by 1 over b. Isn't the reciprocal of 1 over b like 1 over b is just b, right? Or I could write that if I wanted to as b divided by 1 over a. Okay? Well, couldn't I write this as 0 times infinity? I could write that as 0 divided by 1 over infinity. What's 1 over infinity? That's equivalent to 0, isn't it? Right? Aha, so that would equal 0 over 0, right? Or I could write it as, that's one way I could do it, or I could do it as infinity divided by 1 over 0. What's 1 over, oops, sorry. Yeah, 1 over 0. What's 1 over 0 equivalent to? Infinity, right? So that would be equivalent to infinity over infinity. So those would be equivalent to the types of ratios that L'Hopital's rule could address. Okay, is that rigorous algebra? No, you can't do stuff like that. You can't say 1 over infinity equals 0. But in the limit, we know that's what's going to happen. If I have the limit of 1 over x, for example, as x approaches infinity, I know that's going to approach 0, right? I know that if I have 1 over 0 is nothing. You can't do that. You can't divide 1 by 0. That's not defined. But 1 divided by the limit of x as x approaches 0 is going to be an answer that approaches infinity. So you get what I mean when I write this stuff down, right? A limit of the form 1 divided by 0 is going to end up producing an infinite result. Okay? So you get the idea for our strategy then. What could we do here? What are my options? Right? One thing, what do you think? What could I do to this product? Got to make it look like a ratio, to use L'Hopital's rule. Okay, so I could do the limit of x divided by 1 over log x as x approaches 0 plus, or I could do what? Yeah, I could do the limit of log x divided by 1 over x as x approaches 0 plus. Well, based on the colors I chose, which one is definitely better? The green one, right? How come? Well, differentiating 1 over log x, that doesn't sound fun, right? But differentiating 1 over x is no big deal. That's just differentiating x to the negative 1, right? That's easy. Okay, so we'll choose this path. And it is indeterminate. What is the form that this matches? If I evaluate this, the log of 0 plus, everybody, is what? Negative infinity based on our graph, right? 1 over 0 plus is infinity. So I'm getting infinite over infinite here. So that does match, we verified that L'Hopital's rule does apply, right? So let's differentiate. What am I gonna get on top? 1 over x, yeah, the derivative of log x is 1 over x. What's the derivative of 1 over x? Okay, a derivative of x to the negative 1 would be negative x to the negative 2, right? So negative 1 over x squared. Well, again, let's orange bubble that. What's that equal? Yeah, negative x squared over x, which is just negative x, right? Okay, give me 1 to 5 on that last step. I want to make sure you guys follow that right. Okay. I mean, if all I'm doing is flipping and multiplying by the bottom, I could write that as the product of 1 over x times negative x squared over 1. And I just simplified, right? So what's my answer then? What's the limit of negative x as x approaches 0 from the right? Doesn't really matter. I get 0, don't I? Do I really care about the sign of 0? No. It's approaching the value 0. Technically, it'd be a 0 minus, but I don't care. It just equals 0. 0 minus is still just a number very close to 0. Okay? Make sense? Okay. So that's the strategy we have if we start with the indeterminate form 0 times infinity. We got to convert that into either a 0 over 0 ratio, in indeterminate form that looks like 0 over 0, or that looks like infinity over infinity. And then we do what we did before. L'Hopital's rule it. Okay. What about this one? What would I mean, we don't have to do the whole problem, but let's just practice the first step. What would my first step be on this one? Okay, good. We want to leave the sine 1 over x on the top, right? We don't want to do the reciprocal of sine. That becomes a cosecant. We don't want to deal with that. We're going to leave the ugly one on top and take the reciprocal of the simple one, the x. Stick that one on the bottom. So limit of sine 1 over x over 1 over x as x approaches infinity. I guess we want to make sure that that gives us, everybody agrees this would have given us, we didn't check it, but this would have given us infinity times 0, right? Okay. So then we would just go from there. Okay. Do you want to do that one or move on? Raise your hand if you want to go through that. We want to see that one? Okay, let's see it. Okay. So if we differentiate, what's the derivative of sine of 1 over x? Quotient, or it's a product, or I can't talk. Chain rule, right? There we go. Third time's charm. Okay. Cosine 1 over x times the derivative of 1 over x, which we just did. That's just negative 1 over x squared, right? So I would get negative cosine over x squared. That's all in the numerator. Derivative of 1 over x, we just did a second ago. That's just negative 1 over x squared. Well, that's going to work out pretty nicely, isn't it? When I simplify that, if I orange bubble it, rewrite that argument of the limit. Yeah, look, the x squareds are going to cancel, aren't they, when I flip and multiply? And what we said yesterday, we can now see that because I have single fraction on top, single fraction on the bottom, if the denominators cancel, I can just skip that step. I just end up getting negative over negative is positive, and I get a cosine of 1 over x is all I'm left with. Okay, and then we would just take that derivative. Okay, derivative of Do we even have to do that? What am I saying? Take the derivative. We don't take the derivative. And I'm not firing on all cylinders today. We can't differentiate that. We have to check and see if it's an indeterminate form, but it's not. What's the answer? 1, right? Because if I let x approach infinity, what 1 over x just becomes 1 over infinity, which is 0, right? This is just equal to cosine of 0, which is 1.
Why can you not differentiate?
Because L'Hopital's rule says you can only differentiate using L'Hopital's rule if you're starting with an indeterminate form,
Oh,
right? So you'd have to check, like in these last examples, like we used, for example, with this one, we differentiated. Oh, no, we didn't. We didn't have to on that one. This guy, right? We differentiated once and got this using L'Hopital's rule. When we evaluated, that was still indeterminate, so we'll go again. We'll apply L'Hopital's rule again. But as soon as we get to an answer where we're no longer indeterminate, then I just evaluate the limit. I stop with L'Hopital's rule. Just evaluate the limit. Okay. Okay, so what about one like that? So I probably should say this. This is a different indeterminate form. This is the indeterminate form limit of infinity minus infinity. That's indeterminate because we don't know which infinity is bigger if they're growing at the same rate. The answers could be anything from negative infinity to positive infinity with everything in between, including 0, right? We don't know. So what do you think we're going to do there? And my hint is pretty darn similar to what we just did. Yeah. Again, we just need to write that as a limit of a ratio, and guaranteed it's going to be indeterminate, right? Then we're going to have to apply L'Hopital's rule. So we would just get a common denominator. So I'd have to multiply, if we get a common denominator, what am I going to have to multiply this first fraction by? What over what? What's my common denominator going to be? X sine x. So then what's this first term going to become? I have to get x sine x. This has to become, that has to become an x sine x, and that has to become an x sine x, right? So what do I have to multiply this one top and bottom by? Sine x over sine x, right? Everybody see that? So that's really what I'm doing there. I'm multiplying this one by sine x and that one by sine x, which leaves me with a sine x on top minus, there's my minus sign. What am I going to have to multiply this side by? Yeah. That whole thing times x, right? So that's going to give me on the top an x. Okay? Agreed? Now, if I take the limit as x approaches 0, I'm just going to get 0 minus 0 divided by 0. So 0 over 0. It does fit the indeterminate form, 0 over 0. So I would just apply L'Hopital's rule. Okay? If we differentiate the top, derivative of sine x is just cosine x minus derivative of x, 1. On the bottom, What am I going to get if I differentiate the bottom? Plus sine x times 1, right? Something like that. Okay. All right, let's try it. If I evaluate that one at 0 plus, I'm going to get 1 minus 1 is 0. On the bottom, I'm going to get 0 plus 0 is 0. Still indeterminate, right? That still fits 0 over 0. So what do I do? Again, yep. So we differentiate. On the top, derivative of cosine, negative sine x. On the bottom, yikes, right? I'm going to have another product rule. So this part, isn't that just going to give me cosine x minus x sine x? That part? Agreed? I just chose to put the positive one first. So I did cosine times the derivative of x plus x times the derivative of cosine. And then the derivative of sine is plus cosine x, okay, which I could simplify if I wanted to. I could write that as the limit of negative sine x over 2 cosine x minus x sine x. Okay, let's evaluate this one. As x approaches 0 plus, the top becomes 0. Okay, bottom though is going to become 2 minus 0, right? Great. Okay, so I'm getting 0 over 2, which is what? 0. Done. Okay. All right, last form I'm going to show you. And, again, I'm not going to have you do a ton of stuff with these, but I want you to see them this year. And then when you see them again next year, even if you don't remember everything, it'll come back really fast. So indeterminate forms, one of these three types. 1 to the infinity is indeterminate. Okay. Things that look like 1 to the infinity, because it's not really a 1, it's a value that's approaching 1, right? And the exponent is a value that's approaching infinity. So that could be something like 1.1 to the infinity, which would be infinite, right? Or it could be something like 0.9 to the infinity, which would be 0, right? Okay, 0 to the 0, we don't know, right? We don't know if those values are approaching 0. We have no idea what that's going to be. Or infinity to the 0. Okay, if the base approaches infinity and the exponent approaches 0, we don't know what the outcome is going to be. Okay, the strategies for these are really not a big deal. You're familiar with this. We're just going to use the same kind of strategy we would have used before if we had functions that started off as a function to a function, right? Because really what's going on here is we're taking the limit of f of x to the g of x, where f of x is approaching 1 and g of x is approaching infinity, or f of x is approaching 0 and g of x is approaching 0, or f of x is approaching infinity and g of x is approaching 0, right? But ultimately, they're all functions that look like that, function to a functional power. How did we simplify those when we were trying to differentiate stuff like that? We use logarithmic differentiation, right? That's what we're going to do here. We're going to do the same kind of thing. Our first step is just going to be, if we just call this power to a power, if we just call that y, then we're just going to take the log of y, right? And that's going to give us, we're going to end up getting, instead of y equals f of x to the g of x, we're going to get log y equals, by our properties of exponents, the log of f of x to the g of x, I could pull the g of x down in front, right? Just like we did with logarithmic differentiation. So log y equals g of x times log f of x, okay? Then we find out that limit just the same way we did in the last one. I would end up with a product. I'm going to have to turn that into a ratio, right? And solve it using L'Hopital's rule. And that way I'm going to find out what the limit of log y is equal to. And if I know that the limit of log y equals some value, which eventually we're going to get from L'Hopital's rule, then that tells me that if log y equals L, then the limit of y equals e to the L, right? Let's look at this last statement right there. We get down to that last step where we've got the limit of log y as x approaches c equals L, then I have a property of limits that says if the limit of log y equals L, then e to the limit of log y is equal to e to the L, right? And what is e to the limit of log y is the same thing as saying, that's the same thing as saying the limit of e to the log y, which is just y. So we just solve for y. Okay? Right? These are interchangeable by our properties of logs. Now we didn't really focus on those properties, that particular one so much, but I promise you that was part of that list of properties of logs that we had. Okay? So let's look at an example then. Like what if we had something like, what if we started off with y equals x to the x? Okay. And we're taking the limit as, we're going to take the limit as x approaches 0 plus. Okay. We're taking the limit. So really what they didn't actually explicitly state this about, what we're doing here in this problem is we're taking the limit of x to the x as x approaches 0 plus. Well, that looks like 0 to the 0, doesn't it? Right? So what do? Well, we're going to log both sides, right? Okay, so we end up with the limit of log y as x approaches 0 plus equals the limit of x log x as x approaches 0 plus. Okay? Well, this, we've done one like that, right? We're just going to write that as the limit of log x. So just this part, I know we're going to run out of time here, but just this part right here, we're going to rewrite as the limit of the ratio log x over 1 over x, right? So then instead of being 0 times infinity, we've got something of the form infinity over infinity, right? We apply L'Hopital's rule. So this is equal to the limit of 1 over x divided by negative 1 over x squared. Well, that's just equal to the limit of negative x as x approaches 0 plus, which is 0, right? Okay, so then we could go back and say, okay, well, if we know that the limit of log y is equal to, as x approaches blah, 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 is equal to 0, well, then what do we know? Then we know that y is just equal to e to the 0, right? How about that? Really what we're saying is the limit of e to the y, the limit of y equals the limit of e to hand as hand approaches 0. But that's what we're gonna get, which is one. Amazing.
Is that how rule only work for one national?
No, it works for any exponent.
But you log them?
Say it again.
Oh, that's exponent.
That's it. It's just, our basis happens to be an E, but that's just a property of all exponential functions. Yeah. Okay, I went so fast with the last one. We can look at one more of those next time. So there's two assignments. The first assignment is the stuff that's on the AP test. It's just the two racial ones, and the second one's kind of a challenge one. It's all these other indeterminate forms.